how can the same metabolite both activate and inhibit the same enzyme? In this work, we studied enzyme IE1, the first prot E1N in the bacterial phosphotransferase system. E1 sits at the top of a phosphorylation cascade that begins with phosphoenolpyruvate, or PEP, and controls sugar uptake, as well as broader cellular processes including virulence, biofilm formation, chemotaxis, and inducer exclusion. A central feature of E1 regulation is oligomerization. Monomeric E1 has low activity, while dimeric E1 is the catalytically competent form. Binding of PEP promotes dimerization and shifts E1 toward the active state. We first used analytical ultracentrifugation to test how ligands affect this monomer-dimer equilibrium. The data show that both PEP and alpha-Ketoglutarate shift E1 toward the dimeric state. This suggested that alpha-Ketoglutarate could do more than simply compete with PEP. To measure E1 activity directly, we developed a real-time NMR assay based on sophastrosia experiments. In this assay, A1 transfers a phosphoryl group from PEP to HBr, and phosphorylation of HBr produces residue-specific NMR changes that can be followed over time. The key result is that the effect of alpha-Ketoglutarate depends on the oligomerization state of E1. When E1 and PEP concentrations are low, E1 is mostly monomeric. Under these conditions, alpha-Ketoglutarate promotes dimerization, increases the population of active E1 dimers, and stimulates phosphoryl transfer. But under conditions that already favor the E1 dimer, the same metabolite has the opposite effect. When E1 concentration is high, or when PEP is high enough to stabilize the dimer, alpha-Ketoglutarate primarily competes with PEP at the E1 binding site and inhibits activity. This creates a context-dependent regulatory switch. Physiological changes in E1, PEP, magnesium, and alpha-Ketoglutarate levels can determine whether alpha-Ketoglutarate stimulates or inhibits E1. Together, these results show that E1 regulation cannot be understood from ligand binding alone. The oligomerization state of the enzyme determines the functional output of metabolite binding, providing a mechanism for bacteria to tune carbon uptake in response to nitrogen availability. To know more, read our work online.